Hi, welcome to this video. In today's video, I'm going to prove arithmetic mean geometry mean property. Okay, I'm going to apply Jensen's inequality theorem. I already in previous video I proved this one by using the Jensen's inequality for the concave function. Okay, this is concave function. This is Jensen's inequality. This is just special case of this one. This is general proof. Okay, so if you take just 2 points instead to take n points. Okay, so this one is verified. This one as you have here, f of x1 plus x2 over 2 inferior or equal f of x1 plus f of x2 over 2. Okay, so now I'm going to pick up the first inequality, because this one represents concave function. I'm going to pick up concave function. I'm going through concave function, then I will able to prove this theorem. Okay, so now let's pick up a function f of x equal to natural log of x. This is concave function. Concave function. What's the condition for the concave function? Concave function has to be monotonically decreasing, and also the second derivative function has to be negative. Let's try this one. F of x, for example, f prime of x, the first derivative function, equal 1 over x. As you see here, this function is decreasing, is monotonically decreasing. Theorem. Okay, let's consider f of x equal to natural log of x as a concave function. Okay, what's the condition for the concave function? The concave function has its first derivative function has to be monotonically decreasing, and the second derivative function has to be negative. Okay, this is two conditions to have the concave function. Let's try this one. Natural log of x, f prime of x equal to 1 over x. Okay, for all x from open interval 0 to infinity. Okay, so this one, if you take a look at this derivative function, this is decreasing function, because whatever the number you put here for the x, this function f prime x becomes smaller and smaller and smaller. That's mean that the function f of prime of x is decreasing over this interval. Okay, let's try second derivative function. Second derivative function of this one is 1 over x squared. Okay, that's mean this is negative. Okay, this is two conditions are satisfied this theorem. That's mean the f of x is concave function. Okay, let's apply this one in order to prove this theorem, AMGM, arithmetic mean geometry mean inequality property, by using the Jensen's inequality. Okay, we have f of a1 x1 plus a2 x2 and so on until you get the last term an xn. Okay, inferior or equal a1 a sub 1 f of x1 plus a sub 2 f of x2 and so on until you get the last term. Okay, so as you see here, we have this condition a sub 1 equal to a sub 2 and so on until you get the last term a sub n equal 1 over n. Okay, so let's replace this one by a sub n. So f a sub n x1 plus a sub n x2 and so on until you get the last term a sub n xn. Inferior or equal a sub 1. I'm replacing a sub 1 by with a sub n f of x1 plus a sub n f of x2 and so on until you get the last term a sub n f of xn. Okay, so this one I'm going to, as you see here, I'm going to put a sub n as a multiplier. Okay, So f of a sub n x1 plus x2 and so on until you get the last term xn. Okay, inferior or equal, same thing. I'm going to multiply I'm going to multiply a sub n as a, I'm going to put a sub n outside as a multiplier. So this one is giving me f of x1 plus f of x2 and so on until you get the last term f of xn. Okay, so this is equivalent f of so a sub n equal to 1 over n as you see it here. Let's put it. So x1 plus x2 plus x3 and so on until you get the last term xn over n, because Luari put this one a sub 1 equal to a sub 2 to a sub n equal 1 over n. Okay, as you see it here. So this one inferior or equal 1 over n. Okay, f of x1 plus f of x2 and so on until we get the last term f of xn. Okay, so we have this one now. What I'm going to do, I'm going to apply a natural log of x. I'm going to put this function f as a natural log of x. Okay, on both sides. I'm going to apply natural log of x as a function f to be applied on both sides. Okay, so what does mean? Natural log of this sum inside, which is x1 plus x2 and so on until you get the last of x and xn. Okay, over n, inferior or equal 1 over n. So this one I can rewrite it this one can rewrite this on this form. Sum of I goes from 1 to n over n. Okay, inferior or equal sum f of xi over n. I goes from 1 to n. Okay, so now I have this one. I'm going to apply a natural log on both sides as a function f. Okay, so natural log on both sides is giving me sum of xi, I goes 1 to n over n. Okay, inferior or equal sum of natural log x I, for example, over n. N is outside of natural log. Okay, as you see it here. So I goes from 1 to n. Okay, so now if you take a look at here on the right hand side, so if I put this natural log on this form, so this one is goes x1 plus natural log of x2. If I'm putting this one on this form, natural log of, I'm going to distribute this one, natural log of x1 plus natural log of x2 and so on until you get the last one xn. Okay, over n. This one I'm going to apply the logarithm rules, which is natural log of x1 product x2 and so on until you get the last term, okay? Over n. This one I'm going to apply this one equal to x1, x2, and so on, xn, 1 over n, okay? So as you see it here, so I'm applying the natural log rule, okay? So have natural log of the points x, natural log of x1 plus natural log of x2 and so on until you get the last term natural log of xn equal natural log of x1 multiplied by x2 multiplied by x3 until you get the last term xn, okay? Over n. You see this is over n. 1 over n, I can rewrite it on this form again and put it inside of the natural log. If you take this one out, now it become 1 over n. And then you distribute again, okay, backward. You can write it on this form by, okay, forward. You can do it in forward and backward, okay? So now I'm going to take this inequality at the top and continue with our problem, okay? Equal to this one by applying this identity, okay? So this one become x1, natural log of x1 multiplied by x2 and so on until you get the last term, okay? Over n. Also this 1 over n, I can rewrite it natural log of x1 multiplied by x2 and so on, 1 over n, okay? So now natural log of sum of xi, I goes from 1 to n, inferior or equal natural log of x1 and so on, x2 until you get the last term xn, 1 over n equal to natural log of product xi, I goes from 1 to n, okay, 1 over n, okay? Now since f of x, natural log of x, is increasing function, so since f of x equal to natural log of x is increasing function, now I'm going to take off the natural log from both sides. I will not affect this inequality direction, okay? Because the increasing function, so if you have x is inferior, if you have x strictly inferior than y, if you have increasing function, it means f of x is inferior, it means f of x is strictly inferior than f of y, because f is increasing function, okay? If you have x inferior than y, f of x superior, strictly superior than f of y. If you have f is decreasing function, okay? If you have the f decreasing function, okay? So this is very important. The natural log of x is increasing function, so is increasing function, this one. So since we have this function is increasing function, that means I'm going to take off this natural log from both sides, okay? So since natural log of x is increasing function, okay, I'm going to take the natural log off from both sides, okay? So now I proved this inequality. This is a good place where I can stop. Thank you for watching. I will see you in next video. Bye.